Here we have another problem, another differential equation problem, and we have to find the general solution of this particular differential equation. So here it looks as if we're going to have to attempt using the exact method. And for this method, we know m equals y minus x cubed and n equals x plus x cubed over here. So our first step obviously is going to be to try to find whether or not this differential equation is exact, right? So we do that by taking the partial derivative of m with respect to y and checking to see if it's equal to the partial derivative of n with respect to x. If so, then m is equal to df dx and n is equal to df dy, where f of xy is equal to c is the solution to this differential equation. So if this is the case, then we have to solve for f of xy. So let's start by checking. We find that dm dy, let's see, dm dy is equal to the derivative of y minus x cubed with respect to y, which is equal to 1. And if we take the derivative of n with respect to x, that is ddx of x plus y cubed, we find that this derivative is likewise equal to 1. So dm dy is equal to dn dx, which means that this differential equation is exact. So now that we know that it's exact, we have to well, before solving for f of xy, we know that m must equal to df dx and n equals df dy. So in order to solve for f of xy, we can pick either one of these functions to use to solve for f. And the way we're going to do this is, well, let's say we choose this first one here, m equals df dx. So that means that df dx is equal to m, which is y minus x cubed. So y minus x cubed, which means that we have the integral of df is equal to the integral of y minus x cubed dx, which gives us f is equal to, let's see here, if we integrate y with respect to x, we get y times x. We integrate the minus x cubed, we get minus x to the fourth over 4. And then of course we have an additional constant, so a plus c. But it's not just going to be a plus c. This constant is going to be a constant with respect to x. And our constant with respect to x has to be a function of y. So we put plus g of y. So our goal now here is to solve for this g of y so that we can complete the solution for f. And the way we're going to do that is by using the fact that the derivative of f with respect to y equals n. Okay, so df dy equals n, where n is x plus y cubed. So we take the derivative of f over here with respect to y, and we find that df dy is equal to, okay, so this is going to be derivative of yx with respect to y. That's just going to give me x. This vanishes, and then we have a plus g prime of y after taking the derivative of g of y with respect to y. So this equation, this function over here must be equal to, let's see, it must be equal to n, where n is x plus y cubed. So we have x plus y cubed. Okay, so which implies after x and x cancel out over here, this implies that g prime of y is equal to y cubed. And after we integrate, we find that g of y is equal to 1 over 4 y to the power 4 plus a constant. So now that we have this g of y, we are going to plug this g of y back in here to get our full solution for f. And if we do that, we find that f of xy is equal to y times x minus x to the power 4 divided by 4, and then plus g of y. And g of y is just y to the power 4 divided by 4, and then of course plus the constant c. Now remember, we said that our solution has to be of the form f of x plus y equals c, which implies that all of this f of x comma y, f of x comma y equals c, which implies that all of this f of x comma y is equal to another constant, and we'll call that constant b. Okay, so, or better yet, just to avoid confusion, we'll call this first constant c1, and then we'll call this second constant c2. So if we move c1 here, then we find that y times x minus x to the power 4 over 4, and then plus y to the power 4 over 4 is equal to our constant c, and we can write this as our solution to the differential equation. Our next problem here is to find the general solution of this linear first order non-homogeneous differential equation. So the first thing we notice about this differential equation is that we must use the linear method, since this is a first order differential equation and it's linear. So the linear method involves applying the integrating factor, and in this case our integrating factor rho of t is equal to e to the integral of 2t over 1 plus t squared multiplied by dt. Now the integrating factor is a function that you can multiply this equation by, such that this left-hand side of the equation looks like a derivative, more specifically a product rule. Okay, so if we multiply this rho of t to this left-hand side of the equation and the right-hand side of the equation, we find that we have, let's see, y prime multiplied by rho of t plus 2t divided by 1 plus t squared multiplied by rho of t times y is equal to the cotangent of t divided by 1 plus t squared also multiplied by rho of t. Now if you look here, remember rho of t is e to the integral of 2t over 1 plus t squared dt. And if you notice what's next to this rho of t, it's the same function that's inside the integral, which shows that this entire function over here is just the derivative of rho of t. Okay, so this is, we can say this is rho prime of t. Okay, so we can rewrite this entire left-hand side as y prime times rho of t plus rho prime of t times y is equal to the cotangent of t divided by 1 plus t squared all times rho of t. And if you notice, this whole left-hand side now looks like a derivative. A derivative of what? It really looks like a derivative, the derivative with respect to t of y times rho of t, right? Because if you take the derivative with respect to t of y times rho of t, what you end up is y prime. What you end up with is y prime multiplied by rho of t plus rho prime multiplied by y. And so we can say that the derivative with respect to t of y times rho of t is equal to cotangent of t divided by 1 plus t squared multiplied by rho of t. And if we differentiate both sides with respect to t, we have y equals, let me place the rho over here. Y times rho of t is equal to the integral of rho of t times cotangent of t divided by 1 plus t squared dt. And of course, let's put our plus c, our constant, on the right hand side. So we can solve for this y, which is really the solution to this differential equation. So we can write y of t is equal to the integral of rho of t times cotangent of t divided by 1 plus t squared times dt plus c. And all of this is going to be divided by, let's make a straight line here. So all of this is going to be divided by rho of t. Okay, so our solution, our general solution, y of t, of this differential equation is of this form. Now all we need to do here is calculate rho of t, substitute it into this equation, and then solve this integral. Okay, so let's do that. Let's do that here. Let's move this up a little bit here. Okay. So our rho of t is equal to e to the integral of 2t divided by 1 plus t squared dt. If we integrate 2t over 1 plus t squared dt, then what we end up with is ln of 1 plus t squared. That is the natural logarithm of 1 plus t squared. So this is equal to e to ln of 1 plus t squared. And since the exponential and the logarithmic are inverse functions, you can say they cancel out and give you 1 plus t squared. And so we have our rho of t, our integrating factor, and we can make the substitution into this equation. So of course, if we make it into the numerator, we're going to have to solve for this integral part. So let's go ahead and solve for that part. So we have the integral of rho of t times cotangent of t dt over t 1 plus t squared is going to be 1 plus t squared times cotangent of t divided by 1 plus t squared dt. And of course, these two cancel out. And this leaves us with the integral of cotangent of t dt, and which is equal to the integral of cosine of t over sine of t dt. And if we apply u substitution over here, we find that this integral becomes the natural logarithm of sine of t. Okay, so now we have the solution for this integral part, so we can solve for our general solution to the differential equation. So our general solution, y of t, is equal to ln of sine of t plus c, and that's going to be divided by 1 plus t squared, which is our integrating factor here. So our general solution, y of t, is ln sine of t plus c divided by 1 plus t squared.